Let's jump right into this explainer and look at how the seemingly simple diode is actually the ultimate multi-tool of the electronics world. When we first learn about electronics, we're usually taught that a diode is just a basic one-way valve for electricity. And sure, that's true, but it barely scratches the surface of what these tiny semiconductor devices can actually do. Today, we're really going to explore the fascinating, somewhat hidden potentials of the basic p-n junction. We've got a great roadmap ahead for this explainer. We're going to cover rectifying AC to DC, move into full-wave rectifiers, check out the light manipulators, and finally, look at what I like to call the rule breakers. Kicking things off with rectifying AC to DC, and really the core power problem. Let's look at the foundational role of the diode and power conversion. This is the stuff that makes basically all of our modern consumer electronics possible. Here is the crucial issue. The devices we rely on every single day, our laptops, smartphones, TVs, they all demand smooth, steady, direct current, or DC power, to operate. But the power grid, it's out there delivering alternating current, AC power, to our wall outlets. That AC power is constantly reversing direction in a sine wave. Literally, if you fed that raw AC directly into a microchip, total disaster. It would fry. So how in the world do we bridge that gap? Well, we use a process called rectification. And our first solution to this is the half-wave rectifier. By placing just a single, ideal diode between our AC source and the load resistor, we effectively create a one-way street. Think of it like this. When the incoming AC voltage swings positive, the diode becomes forward biased. It essentially opens the gate and allows the current to flow right on through to the load. But the moment that AC wave dips into the negative half of its cycle, the diode becomes reverse biased. It slams shut. The current drops to exactly zero. The net result we get is a 60 Hz pulsating DC voltage made up of only those positive humps. We've successfully stopped the current from reversing back on us. Now, while that half-wave setup absolutely gets the job done, it has a pretty glaring flaw. We are literally throwing away half of our available power by just blocking that negative cycle. Which brings us to our next concept, full-wave rectifiers and how we go about doubling our efficiency. When you compare the two approaches, the efficiency upgrade of the full-wave rectifier is just undeniable. A full-wave rectifier is specifically designed to allow current through the load during the entire input cycle, not just half of it. Because we're actually capturing both the positive and the negative alternations, our output frequency effectively doubles. To put that into perspective, the average value you'd read on a DC voltmeter is literally twice as high for a full-wave rectified voltage compared to the half-wave version. It's just a massive, massive upgrade. So how do we actually pull this off? How do we capture both halves of the wave without letting the current reverse? Well, let's break down one of the most common methods, the center-topped full-wave rectifier, into a few logical steps. We take a transformer with a center top connected to ground, and we use two diodes instead of just one. They basically act as a tag team. Diode 1 handles the positive cycle, and diode 2 tags in to handle the negative cycle. To see how this plays out in action, during the positive half cycle, the first diode is forward biased and conducts the current through the load resistor from top to bottom, while the second diode just sits there doing nothing. But then, during the negative half cycle, the polarities flip. Diode 1 shuts off and diode 2 turns on. And here's the genius part. Even though the current is now coming from that second diode, it is still forced to flow through the load resistor in the exact same direction from top to bottom. We've taken an alternating current and corralled it, forcing it to maintain one single direction. That yields a continuous, unbroken chain of positive voltage pulses. Now, rectifying power is an incredible utility, no doubt, but diodes can do a whole lot more than just direct the flow of heavy electrical currents. Let's shift gears entirely and look at the light manipulators, specifically LEDs and photodiodes. There is this really fascinating symmetry between these two components. They are essentially perfect opposites. Take the light-emitting diode, or LED. When you push a forward-biased electrical current through an LED, electrons cross the junction and recombine with holes, and that action releases energy as intense visible light. Now consider the photodiode. It does the exact reverse of that. When photons of light strike its junction, they transfer energy, creating new electron-hole pairs, which instantly spikes the reverse current. So the LED turns electricity into light, and the photodiode takes light and turns it right back into electricity. And knowing this leads us to a really profound question. What happens if we combine them? What if we build an optoisolator? We can place an LED and a photodiode inside a single, sealed package just facing each other.
When a signal pulses through the LED, it flashes light across a tiny little physical gap. The photodiode sees that light and instantly replicates the electrical signal on the other side. Now, you might be wondering, why go through all this trouble? Well, because it gives us absolute, total electrical isolation. There is zero physical wire connecting the two circuits, it's only a beam of light bridging the gap. This is exactly how a highly sensitive, low-voltage medical monitoring device attached to a patient can be completely, safely shielded from any dangerous high-voltage power surges in the hospital's main electrical system.
All right, so we've conquered power and we've conquered light. Finally, let's explore our last category, the rule breakers. These are special-purpose diodes deliberately manufactured to behave in ways that would, quite frankly, instantly destroy ordinary electronics. The most famous rule breaker of them all is, without a doubt, the Zener diode. Look, if you take a standard rectifier diode and push way too much reverse voltage into it, it's going to hit its breakdown point and just be destroyed. Game over. But the Zener diode, it's heavily doped. That means specific impurities are intentionally added during manufacturing to alter its conductivity. They do this specifically to reduce that breakdown voltage and create a super thin depletion layer, that insulating barrier inside the diode. It is engineered to operate safely in that harsh reverse breakdown region. But why on earth would we want to do that? The answer lies in how the breakdown actually behaves. Once the reverse voltage hits a very specific, targeted point, which we call the Zener voltage, the breakdown curve essentially drops straight down. What this means in practice is that the reverse current can shoot up rapidly, but the voltage across the diode, it remains incredibly, stubbornly constant. Regardless of how wildly the current fluctuates through it, the Zener diode fiercely holds that specific voltage line. This quirk makes it an absolutely brilliant, yet simple component for voltage regulation in power supplies. To round out this rather eccentric family of rule breakers, we have a few other highly specialized components. First, there's the tunnel diode. This thing is so heavily doped with impurities that it exhibits something wild called negative resistance. Normally, as voltage increases, current increases. Simple. But in a tunnel diode, there is a specific operating region where pushing more voltage actually causes the current to drop. This bizarre trait makes them absolutely perfect for oscillator circuits. Then we have the Varactor diode. Because the depletion zone of a p-n junction acts like an insulator sandwiched between two conductive regions, a Varactor is designed to exploit that exact physical property. By changing the reverse voltage, you can actually widen or narrow that depletion zone. You are effectively making a voltage-controlled variable capacitor. And finally, the Shockley diode. This one abandons the simple two-layer p-n structure entirely for a four-layer setup. This allows it to act as an open switch right up until a specific voltage triggers it to violently latch into a low-resistance on state. We've covered a tremendous amount of ground in this explainer today. From smoothing out the harsh, pulsating, alternating currents of the power grid, to safely isolating vital medical equipment using microscopic beams of light, and even bending the very rules of resistance and voltage regulation, we've seen just how remarkably versatile the humble p-n junction can be. It really leaves us to wonder, if we can engineer this much specialized utility out of a tiny, simple sliver of silicone, what other revolutionary capabilities are hiding in plain sight within the basic building blocks we take for granted every single day? Keep exploring and always keep questioning the basics.